Hey guys, so today we're looking at Algebra 3's 5.3 Day 1 notes, starting to get into using trigonometry to find angle measures that are not just in a right triangle, right? Much more widely used concepts going forward here. Now, Day 1 is going to talk about referring to trig functions of angles using the coordinate plane. It's going to talk about determining the sign of trig functions given the quadrant their angle lies in, because that makes a big difference. And then defining and determining reference angles. We will use reference angles on day 2. All right, so we'll talk about them now in today's lesson, and then next lesson on day 2, we will use them to help us out a lot. So let's go ahead and get started. Now, make sure that you're not writing down what's in blue, and if there's lots of text, I'll make sure to indicate, I'll tell you, hey, make sure you shorten this or whatever, so to save you guys some space or some time and space. Assume that all angles have a vertex at the origin of a coordinate plane. All right, this is how we'll be dealing with the explanation of this classification here. Then consider the right triangles created by drawing a line from the endpoint to the x-axis. All right, so here is our two supposed angles. All right, we've got one angle right here, this 60-degree angle, and then we've got this other 135-degree angle. We'll look at the 60-degree angle first. So what we're doing is considering the right triangle created by drawing a line from the endpoint to the x-axis. So here's the endpoint, 3, 8. We're going to draw a line straight to the x-axis. Let me use a darker green here. Okay. So here is our right triangle, right? It's this is one side right here. The other side is this vertical line I already drew, and the last side is this diagonal here. Now, we're looking at this. This is a right triangle, so typical SOHCAHTOA stuff applies, right? Right, so in a right triangle, the sine of an angle is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent of an angle is the opposite side length over the adjacent side length, right? So if this 60 degrees is our theta, right? So if this is theta, then, right, sine of the green angle, so sine of theta is equal to opposite over hypotenuse, right? So let's actually figure out what these side lengths are. We are calling this distance from the origin up to this dot r sub 1, right? That's just a thing we're calling it. Now, what do you call this distance here, right? How would you find that distance, the length of this side length? Well, we can actually count it because we're on a coordinate plane. 1, 2, 3, 4, 5, 6, 7, 8, right? So this is a length of 8. And this number 8 didn't come from, nowhere. It came from right here. This is a value of 8, and if you remember about ordered pairs, the y value here tells you how far up and down you have to go. So this came from the y value created by making this triangle here. And so this is a distance of 8, so this side length has a length of 8. And then our hypotenuse was just called r sub 1, right? So sine of theta is opposite over hypotenuse, which is 8 over r sub 1, right? That's what that says right here. That should make sense. This is just opposite over hypotenuse. Now, this can be broadened to be y over r, where we say that r is the diagonal's length, or the length from the origin. So r is going to be the length from the origin to the end point of whichever ordered pair you're looking at. So this would be a length of r, right? Or say instead of having 3, 8, we had some point over here, right? Well, then this distance here would be considered r, okay? Now, moving on. Sine of the right angle can be found the same way, or it could also be found using reference angles, which we'll discuss later. So you've got this. To find sine of this, it would be y over r, right? Where we've got y, the y value here, over r, which would be r sub 2, right? And for now, that explanation will have to suffice. We will talk more about how you can get this in a different way when we talk about reference angles. So far, we're talking about how we could find the sine of an angle or the cosine of an angle by where the angle is formed using a point on the coordinate plane. So they give you a point on the coordinate plane and they say you're going to draw an angle in standard position with the initial side on the x-axis and the terminal side connecting this point or whatever point they give you, and then asking you to find trig functions. And then you would use this method, right, that sine is y over r. Well, the rest of the trig functions can be found the same way. So if sine is y over r, right, that's opposite over hypotenuse, cosine would be x over r. And let me explain why if you're not picking this up, which is totally fine. X over r, remember, cosine of a right triangle, like cosine of an angle in a right triangle is supposed to be adjacent over hypotenuse, right? Well, and we're calling it x over r. Going back up here, look at our green triangle here. If this is the theta we're interested in, the adjacent side would be this length here. This would be the adjacent side. And that would be actually a length of 3, and it came from this x value, because this x value tells us how far left and right you go from the origin, right? And then r, again, shows up because r is the hypotenuse, because cosine is opposite or is adjacent over hypotenuse. The hypotenuse, again, is r. So it should make sense that cosine of theta would be x over r, because x represents the adjacent side length. Then tangent is y over x, which is basically exactly like opposite over adjacent, right? As for the remaining 3 trig functions, they are exactly like you'd expect. They're just the reciprocals of their own functions, right? So cosecant reciprocal of sine, secant reciprocal of cosine, cotangent reciprocal of tangent. Now, here's an actual example. Let P equal the point -3, -5, right? And that's a point on the terminal side of your angle. So find each of the 6 trig functions of your angle. Step 1, find r using the Pythagorean theorem. Remember that on all these computations, r is involved, right? We've got a bunch of r's showing up. And previously, right, I wasn't mentioning how to find r, but if you know this length, right, you know this length, and you know this length, that means you know the 2 side lengths of a right triangle. Well, you can find the hypotenuse easily using Pythagorean's theorem. And that is what it says to do first. Find your r value using the Pythagorean theorem. So if this represents x, or one of your side lengths, and this is another side length, and the Pythagorean theorem is like a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse, then these two would act as your legs. And so you'd have -3 quantity squared plus -5 quantity squared is equal to, and we're not calling it c because we're calling it the r value, it is r quantity squared. R is like the length of the hypotenuse there. And so you'd work this out. So you'd get, 9 plus 25 equals r squared. So 9 plus 25 is equal to r squared. And so 9 plus 25 is 34, and so that equals r squared, and you get rid of the square here by square rooting both sides. We will ignore the plus or minus, right, because this r represents a length of a side length, and it can't be negative, so we'll ignore that. And so you get r is equal to the square root of 34. You might be thinking, ew, the square root of 34. But that's okay, right? You should try to get more and more comfortable with answers that are not, whole numbers and that kind of thing. Now, so that's our r. Now we're going to write the trig functions as they appeared on the last slide. So this is the last slide. It's the sine of an angle. Sine of the angle is y over r. Cosine of the angle is x over r, and so on. And we're just going to do exactly this. Now, something to point out. I'll draw this, -3, -5. All right, so we've got, I'll draw a coordinate plane. And it was -3, -5. So -1, 2, 3, -1, 2, 3, 4, 5. So we're looking at something like right here, right? So we are interested in, right, what we're talking about is the trig function of the angle that is formed like this. This is what we're talking about. This angle, if you're wondering, what are we finding? If this was theta, what we are currently doing is finding all of the trig functions for theta here. So sine of theta is equal to y over r. R we found to be, right, the square root of 34. Y is -5 and x is -3. So going through here, -5 over the square root of 34. Done. Cosine of theta is x over r, which is -3 over the square root of 34. Done. Tangent of theta is next on my list. That is y over x. And so that would be -5 over -3, which would be 5 over 3. And then cosecant of theta is the reciprocal of sine, so that would be radical 34 over -5. Then secant of theta is the reciprocal of cosine, which would be radical 34 over -3. And finally, cotangent of theta is the reciprocal of tangent, which would be 3 over 5. I remember that, sine and cosecant are reciprocals, cosine and secant are reciprocals, and then tangent and cotangent are reciprocals. Okay? Now, that's it. You're done. You have found the trig values for each of the angles. Now, don't write any of this down. Okay? Write the underlined portion down, and then, so pause the video here, and write down the underlined portion here. And then resume the video and listen to me explain what's happening. And then once we get down to here, you will write this down, okay? So, first off, determining the sign, and I mean sign as in S-I-G-N, and this sign is talking about positive or negative, right? Determine the sign, not S-I-N-E, which is the trig function. Determining the sign of trig functions given the quadrant their terminal side is in. Okay, so remember on the unit circle, so imagine we had our unit circle here, right? So unit circle, where we had a bunch of ordered pairs, right? Bunch of ordered pairs all the way around the thing, right? If you've got your unit circle, you can see we had tons of ordered pairs all around. Well, the typical coordinate plane, it should make sense, right? This is something we've definitely dealt with, is that up here in quadrant 1, we've got positive x's and positive y's, right? Because you're going in the right direction, the positive direction for x and the positive direction for y. Over here in quadrant 2, we've got negative x's, but positive y's, because from the origin you went left in the negative direction for x and up, which is in the positive direction for y. Now, over here, down here, in quadrant 3, we've got negative x's and negative y's. We went the negative direction for x to get down here and the negative direction for y to get down here. And down here in quadrant 4, we've got the positive x's and negative y's. All right? Now, this is where, if you keep thinking about sine as y and cosine as x, it should follow that every quadrant where x is positive, sine would also be cosine would also be positive. If cosine of an angle is talking about it's like x, right? And then it would make sense that cosine of the angle would be positive if x was positive. So in quadrant 1 and 4, x is positive. So quadrant 4, cosine is positive, and quadrant 1, cosine will be positive because all of them are positive. Then sine of an angle, right? Sine of an angle is the y value at the ordered pairs for around the unit circle. So if the y value is positive, the sine of the angle will be positive. Well, quadrant 1 and quadrant 2 have got positive y's, and so they would have positive sines. So cosine would be positive in quadrant 1 and quadrant 4, here and here, because we're on this side of the origin, right? And then sine would be positive where the y is positive, so that's up here, aka quadrant 1 and quadrant 2. Then tangent of theta, that is y over x. So now you have to think, how can a fraction be negative? Well, the answer is there's two choices. Either neither, so one choice 1, neither x or nor y, right? I don't know how you do this. Neither x or y. I don't care. Neither, x and y. Actually, why do I put this? I should just put x and y are positive. That's much better. X and y are positive. That's the first situation where tangent of an angle can be positive. If y and x are both positive, because a positive number divided by a positive number is a positive number. Then option number 2 is that x and y are negative, because if you have a negative over a negative, that is positive again. So sine is positive where y's are positive, which is quadrant 1 and 2. Cosine is positive in 1 and 4. Tangent is positive in the quadrant where x and y are positive, so that is quadrant 1. But also where x and y are negative, which is quadrant 3. You might be wondering, what in the world are we even doing? We're developing shortcuts to figure out how to determine the trig value or trig function of an angle, right? So next we've got the cosecant, secant, or the cosecant, secant, and cotangent work the same ways, right? So it should follow that in quadrant 1, all of the trig functions are positive. In quadrant 2, sine is positive, and therefore cosecant is positive, but the rest of them will be negative. In quadrant 3, the positive ones are tangent and cotangent, and the rest of them are negative. And then in quadrant 4, cosine and secant are positive, and the rest are negative. Now, here is where we get to the part where you're going to write a phrase to remember which quadrants have positive trig angles. This is the real thing to remember. You might remember this statement, but if you don't know what it means, then it's not helpful, right? So the phrase is all students take calculus, and it is talking about which trig functions are positive in which quadrants. So all students take calculus. This is typically written like this. All students take calculus. So this is talking about quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And the all part means that all of the functions are positive in quadrant 1. So these go in order of quadrant 1, 2, 3, 4. S means that sine is positive, as well as cosecant, right? Cosecant, right? Sine and cosecant are positive. The rest are negative. So these are telling us which is positive. So then, by process of elimination, all the rest must be negative. Take is talking about, you're looking at, by the way, you are considering the first, wow, that is the wrong tool. We are considering the first letter of these words. All students take calculus, which is, a lie, but, whatever. So the S means that the sine is positive. The T here in quadrant 3 means that tangent is positive. Tangent is positive, as well as cotangent is also positive. And then the fourth quadrant, calculus, that would mean cosine. And so in quadrant 4, cosine and secant are positive. Now, let's go ahead and use this information. If tangent of theta is less than 0, right? These are like little puzzles. I like them. If tangent of theta is less than 0, so tangent of theta is negative, right? And cosine of theta is positive. Name the quadrant or quadrants in which angle theta could lie, right? Because angle theta could be, right, here could be theta, or here could be theta, right? This could be theta, or we can go all the way around here. Maybe this is theta, right? If we know that tangent of theta is negative and cosine of theta is positive, let's figure out where theta could lie. So remember, we've got all students take calculus. So this is a process of elimination, so try to follow along. Tangent is negative, which means that quadrant 1 has all functions being positive. So if they're saying that tangent is negative, it cannot be in quadrant 1 because everything in quadrant 1 is positive. So this is out. Actually, let's use something else for that. This is out, right? Next, it says that tangent is negative, right? So that means quadrant 3 is also out, because in quadrant 3, remember, each of these letters represents the functions that are positive in these areas. In quadrant 3, tangent is positive. So if our tangent is negative, nowhere in here could theta lie, because theta in anywhere down here, when you give theta, when you take tangent of theta, it'll always be negative. Or excuse me, it'll always be positive. So this is also out because tangent is supposed to be negative. Moving on, cosine is positive. So this is the only quadrant that cosine, this is the only quadrant left that cosine could possibly be positive in, because the two quadrants that cosine is positive in are this one here and this one here. All of them and then cosine are positive. So that means the answer has got to be quadrant 3. So your answer is Q3. Very good. Look at that. I like problems like this. Moving on. We're not done yet, but I'm moving on to our next topic, which is reference angles. So now that we've got this done, right, you'll have problems like the one we just did, by the way, in your textbook or in your homework. Reference angles. Reference angles are positive acute angles obtained by drawing a line from the x-axis to the endpoint on the terminal side of the angle. So imagine you've got this angle theta, or we'll call this, I guess there's already a theta here, right? So imagine we've got this angle and it's 135 degrees. Here's the terminal side. It wouldn't matter if you ended here or way out here, it doesn't matter. If you were to draw a line down to the x-axis or up from the x-axis, whichever way, you will create a reference angle. So angle theta here is the reference angle. So theta is reference angle. All right, so we got theta being the reference angle here. Reference angles are super important in trigonometry, and we're going to start talking about them now. Angle theta above, wow, I already wrote that down, is the reference angle. Right, so far so good, right? We can actually determine what is theta, because all the way around to this spot here would be 180 degrees, but 135 of it is already being taken up, so it would be 180 minus 135, and that should get you 45. So this reference angle, theta, is 45 degrees. Now, here is the kicker. Actually, I'll save that for later. All right, so we'll talk about why reference angles are important here in just a little bit. So, determine the reference angle of a 300-degree angle. So this is our first example. Determine the reference angle of a 300-degree angle. So our 300-degree angle looks like this. Yoink. Here's your 300 degree angle. Now, remember, to draw a reference angle, you draw a line from the x-axis to the end point on the terminal side. So from here down to here, it's got to be a straight line, straight up and down, right? The shortest distance between, if you're going to get technical, it is the line that is the shortest distance from the endpoint to the x-axis. So this would be the line. So this angle here would be theta. All right. Theta is always formed from, it always touches the vertex of angle theta, or the reference angle, is always the origin. That's, if you're wanting to be nitpicky and have a definition, that is what I would say. I would say that the vertex of the reference angle is always the origin, right? That's something to point out. Now, we have to figure out what is the reference angle. So by looking at this, hopefully you can determine, without me explaining it, what angle theta is. Right? And if not, try to think about it, right? If this is, if this is 300 degrees, this would be the rest of the rotation all the way around the circle. So what would it have to be? Right, the answer is 60. So it'd be 360 minus 300, which would be 60 degrees. Now, so that would be your reference angle theta. Now, moving on. There's going to be a lot of words here. Feel free to just try to absorb this and then do it in practice for the examples, or write it down, whichever you prefer. But there's a lot of words. Finding reference angles for angles greater than 360 degrees or less than 360 degrees. So step one can be boiled down to finding a coterminal angle, because it says add or subtract 360 degrees or 2 pi radians from your angle until you have a coterminal angle that is between negative 360 degrees and positive 360 degrees, or negative 2 pi and positive 2 pi. This is basically finding a coterminal angle that we can relate to, right? One that's not 10,000 degrees, something that is within the realm of understanding one rotation, right? One rotation this way or one rotation this way. Right, one rotation going that way, or one rotation going this way. Now, that's the first step. Draw that coterminal angle and look to find the reference angle. That's it. So, find the reference angle of a 580 degree angle. So here is our XY plane, right? And now we're going to start adding or subtracting 360 to get an angle that we can deal with. So obviously we're going to subtract 360 degrees because you don't want huge angles. So you want to lower this value. So it'll be 580 minus 360, which is going to give you 220. So your coterminal angle is 220 degrees. Then, right, so first off, let me draw a 580 degree angle. A 580 degree angle will go all the way around once, and then go around again by 220 degrees. Oh man. Which would look like this. All right. Something like that. So this would be the full 500, this would be the full 580 degrees. Might be a little tiny. Right? That would be the full 580 degrees. Then we found the coterminal angle, and this was the coterminal angle. It was just 220 degrees. That's not a good color for this. It was just 220 degrees, like this. So this, just this distance, was the coterminal angle. The reason why we can compare these so well is because the trig functions of angles and coterminal angles will always be the same. So sine of 580 degrees should be the same as sine of 220 degrees. Now we look at the reference angle. The reference angle is found by taking, the endpoint, wherever it is, and drawing a line to the x-axis, straight line. All right, let's go straight there, creating a right angle. So say this is our right triangle. The reference angle is found from the x-axis, right? So you got this triangle. This would be the reference angle right here, theta. So now we have to figure out what is theta. Well, if this blue angle is 220 degrees, and then this red distance here, so from here all the way to here, is 180 degrees, and we're interested in finding the remaining piece from here down to here. That would be whatever the difference is between 220 and 180, because you've got to add a number to 180 to get the full 220. So the answer would be 40, because you'd take 220 minus 180, and you'd get 40. So that is the reference angle. Now, find the reference angle for theta when theta is 8 pi over 3. 8 pi over 3. Well, 8 pi over 3 is currently more than 2 pi. It's more than a full rotation. So what we want to do is we want to take that and subtract 2 pi from it, which is going to look like this. 8 pi over 3 minus 6 pi over 3 to get a common denominator, because these two things, in case you guys have forgotten how to add and subtract fractions, these two things are the same. So I've just rewrote 2 pi, and this is 2 pi over 3. So our coterminal angle is our coterminal angle is 2 pi over 3. Now, to find our reference angle. Well, we need to determine where is 2 pi over 3. Well, this is where the unit circle came in. Every pi over 3 is 60 degrees. So 1 pi over 3 would be 60 degrees. So that'd be 1 pi over 3. Another pi over 3, another 60 degrees, would be, right, so this would be 2 pi over 3, which is what we're after. So this angle here is 2 pi over 3. Now, what is the reference angle? Well, the reference angle would be this distance here. It would be whatever quantity would be necessary to finish out to get to pi. So remember, this rotation, right, you gotta watch this. This rotation is 2 pi over 3, but the entire half rotation is 1 whole pi. So if we're looking for this distance here, and this would be pi, but then the distance we've already traveled is 2 pi over 3, it should be 1 pi over 3, because if you take 2 pi over 3 and added another 1 pi over 3, you would get 3 pi over 3, which would be just pi. So that would get you to the 180 degree angle, right? Or alternatively, you could think, you know, if the full distance is 1 pi and you're taking away this much, this rotation here, then you'd have 1 pi over 3 left over. So either way, however you want to think about it, the reference angle here, theta, is actually it's we've already got a theta. We'll call this alpha, is going to be man, my alphas have gotten really bad lately. I haven't done an alpha in a long time. That's better. Is going to be let's see here. What was it? Pi over 3. That's right. Okay. Hey, here's your homework. So just as a point in like to point this out, these lessons are going to start getting longer, right? They're going to start off at like 34 minutes, which is what we're at now, and I anticipate that we're going to have a lesson that is like, in chapter 9, there's going to be some lessons that are 50 minutes probably, honestly. And you know, I mean, that's why I'm going to give you multiple days to work on it. Anyway, there's your homework. Follow the instructions, use the unit circle on the ones that I'm indicating you should use them on. And I will catch you on day 2.